Hi, this is the third lesson of topic 12 on magnetism and the motor effect. And this lesson extends what we learned in the previous lesson on current carrying wires. If you're unsure about current carrying wires and the magnetic fields they produce, go back and watch that video. Now, what are motors? Motors are instruments that convert electrical energy into mechanical energy. And they're used in our everyday life, especially in cars, especially in electric cars. So in this case, the electrical energy from the battery is converted to mechanical energy in the motor. And the motor effect, that's what this lesson's about, governs how that happens. The motor effect governs how motors work. Now let's take a closer look at what the motor actually looks like. Now the current carrying wires produce a magnetic field, and this magnetic field interacts with the permanent magnets in the motor. This causes the coils to rotate. So in this case, the electrical energy causes the rotor coils to rotate, and that occurs as electrical energy from a power source or a battery is supplied. So as we can see here, we have a battery which we are going to introduce into the circuit, and then the wires present in this magnetic field will begin to rotate. So we can see that the magnetic field is from north to south, and when a current carrying wire is present in this magnetic field, it experiences a force, like so. And this force causes the coil to rotate. This offers us a better look at what this looks like. This is known as the motor effect, and that's what this lesson's about. Let's take a closer look. Here can show us how a current carrying wire experiences a force in a magnetic field. So here we have a magnet, and here we have another magnet. And this setup here, when attached to a power circuit or a battery, will carry current. However, this isn't fixed in position. This rod isn't fixed in position. These are conductors, of course, so it does conduct electricity, but this rod here isn't fixed in position. Let's see what happens when this metal component is hooked up to a power supply. So as you can see, it's not fixed in position, but these are all conductors, so it will absolutely conduct electricity and will carry current. Now let's see what happens when we attach this to a power supply that we can see here. As soon as the circuit's complete, that rod experiences a force and begins to move. Let's see what happens if we remove the magnetic field by removing the magnets. We can see that the component no longer experiences a force. It's important to note that this force is only experienced due to the magnetic field produced by the current carrying wire interacting with the magnetic force and the magnetic field lines of the permanent magnets in this system. This is a screenshot of the clip we just watched. The direction of current flow was in this direction. The direction of the magnetic field was in this direction, from the bottom magnet to the top. And the force the wire experienced, the direction it moved in, its motion, was in this direction. As you can tell, these are all linked and they're all 90 degrees to each other. In fact, they're all linked by Fleming's left-hand rule. So if we make our hand into this shape here, our thumb represents the direction of motion or the force experienced by the wire. Our first finger represents the direction of Our first finger represents the direction of the magnetic field, and our second finger represents the direction of current flow. And as you can see, all three are perpendicular to each other. Let's try it out in this case. Going back to our screenshot from before, does it work? Use your hands to see if you can match what's happening here, where our magnetic field lines are upwards, and that should mean our first finger is pointing upwards. Our direction of current flow is into the screen, and therefore the direction of motion or the direction of force is to the right. This is what it should look like. So, if you take your hand, the direction of the magnetic field lines is upwards, current is into the screen, and motion is to the right. Let's take a look at that one more time. Let's try another one. In this case, we're given the direction of the magnetic field lines from here to here, from north to south. Remember, magnetic field lines always move from north to south. And we're also given the direction of current flow in this direction, using Fleming's left-hand rule. In which direction will the wire move? Pause the video and see if you can figure it out. Okay, so our first finger should be pointing to the right. Our second finger should be pointing towards the screen or into the screen. And therefore, our thumb will be pointing downwards. Therefore, the motion of the wire or the force the wire experiences is downwards. Let's try another. In this case, the wire experiences a force upwards. In which direction is current flowing? Pause the video and see if you can figure it out. Our first finger, representing the magnetic field lines, should be pointing to the right. As our force is upwards, our thumb should also be pointing upwards, as that's the direction of motion. And as a result, our second finger, representing the current flow, will be pointing towards us, out of the screen. Let's try one more. In this case, try and identify the direction of the magnetic field lines and therefore the magnetic poles on the magnet. We're given the direction of current flow, downwards, and we're given the force that the wire experiences, coming out of the screen. Using Fleming's left-hand rule, pause the video and identify the direction of the magnetic field lines. And from that, what's the North Pole and what's the South Pole? So in this case, our current is pointing downwards, so should our second finger. The force the wire experiences is coming out of the screen. Therefore, our thumb, which represents the motion, should also be pointing out of the screen. That leaves our first finger to show the direction of the magnetic field lines. From this we can see that the magnetic field lines are in this direction. And as we know, magnetic field lines flow from north to south. So our north pole is on the left and south pole is on the right. Hopefully you've got the hang of it by now. And as you can see, Fleming's left-hand rule really isn't too difficult. But practice makes perfect. Here's 4 more examples. In each case, identify the force experienced by the wire. Pause the video and see if you can figure out each one. So, in the first one, the force is downwards. In the second one, the force is upwards. As you can see, the only difference is the direction of the magnetic field lines. In this case, moving from right to left. In the third one, the direction of the force is also upwards, because in this case, the direction of the current flow has also changed, along with the magnetic field lines. And finally, we have a downward force. Now, how does this relate to the motor effect? Here we have a coiled wire like we saw at the beginning of this lesson. So as we can see, current flow is in this direction on this side of the wire, or this side of the coil, and on this side, current flow is in this direction. Try and predict the direction of motion of this side of the wire as well as this side. Pause the video and see if you can figure it out. As you know, this coil is a current carrying wire and will produce a magnetic field. This will interact with the field of these permanent magnets. And since this current flow is at right angles to the magnetic field, it will also experience a force right angle to the magnetic field lines and the current flow. We can identify the direction of this force and the direction of this motion using Fleming's left-hand rule. Hopefully you figured out which side is going to experience a force in which direction. So, the left-hand side will experience a force in a downward direction. That's because our second finger, showing current flow, should be pointing towards the screen, and our magnetic field lines should be pointing to the right, leaving our thumb pointing downwards. And on the other side, it's the opposite. Just simply switch your hand around. Now your second finger should be pointing towards you, and your thumb pointing upwards. Now, as the coil experiences this force in this direction, the coil begins to rotate. When the coil's in this position, it actually experiences a force in the upward and downward direction, like so. There is no force to keep the coil rotating. And the only way to keep the coil rotating, like we have in a motor, is to change the direction of current flow. To do that, we use a split ring commutator. This is an instrument that allows the current flow to change as the coil rotates. You don't need to worry about it too much and the mechanics of how it works, but this diagram should show you pretty easily. So as you can see, current flow is in this direction. But as the coil rotates, like so, so does the split ring commutator. Now current flow is in the opposite direction, flowing from this side. This changes the direction of the current flow and the direction of the force, and this allows the coil to keep rotating. Finally, based on our previous lesson, How could we actually speed up the electric motor? How could we increase that motion? And how could we increase the magnitude of that force? Pause the video and see if you can remember. There are three things we can do. The first is that we could increase the current flow. We could also increase the number of coils. And finally, we can increase the magnetic field strength. That's it for this video. I hope you found it useful. If you have any questions, please do ask.